Okay, conventional wisdom for single processors. These are things we all learned when we studied real-time systems for the last few decades, and people wrote hundreds or maybe thousands of papers on these things, and I didn't put up their priority inversion is bad, but that's another one that you could add to the list, okay? So here's some of the things people may even take for granted. Priority doesn't affect total completion time. If you have one processor and you have a set of work to do, it doesn't matter what order you do it in, it takes the same amount of time to finish it. All you can affect is which one gets done earlier. If you priority certain ones, give them preference, they get done earlier. But it doesn't affect how long it takes to finish. Not true for multiprocessor systems. EDF scheduling is optimal for meeting deadlines. True for single processors, not true for multiprocessor systems. Deadline monotonic scheduling, or rate monotonic if you talk about periodic tasks, is optimal for fixed task priorities. True for single processors, not true for multiprocessors. The famous critical zone result, it says if you have a bunch of periodic tasks or sporadic tasks, and you start them all together at once, you'll have the very worst case response time for every task exhibited in that case. That's called a critical zone or critical instant. Not true for multiprocessors in general, at least for sporadic tasks. Okay, so these are all things that are the foundations of a lot of the work on single processor real-time scheduling. They're just not true for multiprocessors. So here's some examples to illustrate those cases. Okay, so here is a set of jobs, and they have deadlines shown here. The arrow's the deadline. It shows the arrival time and the deadline. Okay, so I execute these according to the deadlines. It puts the yellow one and the green one first, whether that be pure deadline scheduling or deadline monotonic at the critical instant. That's what I get. And look, it takes till here to complete the pink one, J3. But if I change the order, I can get J3 done quite a lot earlier. And maybe it makes this deadline now, and it didn't make this deadline there. So EDF and deadline monotonic are obviously not optimal for multiple processors. The critical zone. I mean, here is all the tasks released at once, and there's their deadlines, and they finish there. I take this deadline, this release time is shifted earlier, and whoops, J3 is going to finish way out there. Okay, so no critical zone. Now, most of the work that has been done on multiprocessor scheduling is based on a generalization of the same ideas as single processor scheduling, but a lot of the details are changed because of the more relaxed environment. The basic arguments go like this. We find an upper bound for the maximum demand of processor time that a given job can make between the time it's released and the time it's due, the deadline. We then figure out how much interference there can be during the same interval that prevents that job from being executed. And the interference can be caused by various things. It can be caused by preemption from other jobs. It can be caused by blocking and so forth. We figure out the maximum interference so we can get a bound for that. And that tells us then, this interference tells us the supply of computer time that's available for that job. It's the size of the scheduling window minus the interference. And we just do supply versus demand. And if the supply is less than the demand, whoops, I got it backward, didn't I? Sorry. If supply is greater than demand, the job will complete within its deadline. The difference between single processor and multiprocessor, one of the big differences is this. On a single processor, the only interference we can have is linear in a sense, and that is if there's any job executing, then the job we're concerned about is prevented from executing. So every time anything else is running, our job of interest is being delayed. And it turns out that there's this concept of what they call work-conserving scheduling algorithms. A work-conserving scheduling algorithm is one that never idles a processor unnecessarily. That is, if there's work, it runs something. And that turns out for a single processor to be enough to guarantee there's no idle time up to a missed deadline. So we never miss a deadline unless there's some idle time. And that's the result that allows us to do most of our analysis. We look at the deadline, we see everything's busy between here and here. That tells us something about how much demand there has to be to cause interference for the job that we're trying to execute. On a multiprocessor, life is not quite so nice. we can have lots of idle time and still miss deadlines. What matters, though, are these blocks of interference. And so wherever there's interference, all processors have to be blocked in one way or another if we're talking about preemption. Now, if we're talking about other kinds of blocking, that's not true, like locks, say. Now, this changes all of the equations quite a lot because the level of interference that's required to cause a task to miss its deadline is much less in this model. All these yellow bits here could be ignored as far as I'm concerned. They could be all idle time. We could still miss a deadline. Okay, so some of the changes that we're going to see as we go from a single processor to multi-processor, now we have a two-dimensional scheduling problem rather than a one-dimensional scheduling problem. We're having to fill in a matrix, really, rather than a line. Work conservation is not enough. And in fact, the optimal schedule for short deadline, the nearest deadlines we're trying to meet our close deadlines may actually cause us to miss later deadlines, which is not the case on a single processor. On a single processor, we can always concentrate one deadline at a time. And if we make that deadline, we go to the next one. And it's never, making a local deadline is never going to force us to give up on a later deadline. The most important fact about multiprocessor scheduling is this one. The bottom line on multiprocessor scheduling is to keep all the processors busy as much of the time as you can. You don't have that problem with single processors. Like I said, if you have a deadline, a job is released and a deadline you want to make, you're going to make it unless the processor is busy all of that time. On a multiprocessor, because of the picture we had before, it's these empty spaces that are causing us problems, potentially missing deadlines. We need to fill in the blanks if we want to get good scheduling results. In the short run, there may be local things we can do, but in the long run, maximizing throughput is the name of the game. Locks have a lot larger impact, too, on multiple processors, because a lock on a multiprocessor can force a whole processor to be idle. It could force multiple processors to be idle. Whereas on a single processor, when a lock is held by one process, one thread, say, it's because another thread is running, using it. Not necessarily the case on a multiprocessor. And so priority ceilings don't help. And particularly, they don't help prevent deadlock. We still have deadlocks, too. Another factor where things start to get ugly on multiple processor scheduling is migration. This is the first inkling that people actually talk about this in the literature. The other thing is, when I mention later, I don't think have been talked about. I think it's like the emperor's new clothes. But you'll see talk about migration costs. And people argue we should use partition scheduling because we don't have to migrate jobs from one processor to another. And other people say, oh, no, we get better utilization of the processor by doing global scheduling. And so we get into debates about what is the migration cost, moving a job or a task from one processor to another. And that could happen when it's preempted or just when the job finishes and then we wait and the next job comes. It could run on a different processor. These costs come from the communication delay. If we want to preempt or move something, we have to talk to the other processor, talk to the kernel on the other processor to tell it to do the switch. We have to evict the job we're preempting on the other processor, which means some overhead. And then the big one is when we load the new job, we have to possibly reload the cache on the processor that it's moving to. And those could be pretty sizable overheads, or not. It depends on the machine. So this has been an argument for partition scheduling as opposed to global scheduling, and it's often used as an argument against global scheduling. In the theory, people have modeled this by the way they model preemption costs. We'll say, I'll do the analysis ignoring this cost, and then I'll go back and fudge the analysis by adding a constant factors, a constant additive constants, rather. So I can add a constant to the worst case execution time to allow for the fact that it's going to be increased by the migration cost. We already do this for preemption costs, and a preemption cost and a migration cost occur at the same instant. It's just whether we're switching tasks between processors or just switching tasks on the same processor. But interestingly, on some shared cache machines, experiments have shown that the migration cost is less than the preemption cost. Or the cost of migrating is less than preempting later. Because cache work has to do not just with moving from one processor to another, but it has to do with, even on the same processor, what's happened between times. If you've been preempted and another task runs, it's going to dirty the cache. When you resume, you're going to have to reload the cache anyway. If it's dirty enough, you might as well resume on another processor. It makes no difference. If it hasn't been dirtied very much, then it's cheaper to resume on the same processor. If it's dirtied enough that you're going to have to reload it anyway, you save time by starting right away on another processor than waiting until you have a chance to run on the processor you run before. So complicated, interesting trade-offs. And they have to do a lot with the kind of cache you have. If you have shared cache, then there may not be, it's all one cache anyway. It doesn't matter where you run, if most of the cache is shared anyway. OK, so these migration costs, though, are really just the tip of the iceberg of the problem here. This is the first little bit of the ugly side of architecture starting to pop up. So the actual migration costs are going to be very highly dependent on the architecture, like how much of the cache is shared, how fast is the interconnect between the CPUs and their caches. Between one cache and another, we have to move data between the caches. Is the cache consistency maintained by the hardware? Isn't it maintained by the hardware? And what's happened between the events, between the time the task stopped executing and the time we're getting ready to migrate it? OK, so now some sampling of the results. OK, so we build our foundation, and now we have this beautiful house that we built on top of it that looks very nice. There are lots of results. Thousands of papers, I dare say, at least 1,000. I don't know. How many do you think, Ellen? More than 1,000 papers, I think, on the subject. There's static scheduling results. These are really old, well-known results that date back to the 70s. And basically say, no matter how complicated the schedule, no matter how many constraints you put on the schedule, no matter how many processors there are, no matter how complicated the model is, it's still finite if they're all cyclic tasks. And we can beat it to death by brute force and build a cyclic schedule for it, a static schedule. It amounts in complexity similar to the bin packing problem, but once you recognize this NP hard and you don't go for optimality and look for a heuristic, you can get pretty good results. People have done experiments running things through, and they get, on the average, much closer to optimal results than the worst case analysis shows. And even that's not terrible. These should not be forgotten or neglected, because I'm going to argue in a little while that from multi-core processors for some applications, it may be time to go back to the future, that this is the right way to go if you really want reliability, because it's the only way you can guarantee some things. In particular, if you get into details that are affected by the interactions of the tasks in time, the only way to get deterministic repeatable behavior is to schedule them statically. And it's the only way to really optimize.